let's now use the fundamental theorem of calculus to find some more definite integrals, maybe ones that are a little more involved here. So this one here, I can use the power rule because I can split this up over a common denominator. So I get like x squared over square root of x plus 1 over the square root of x. And then I can rewrite this as this would be x to the 3/2, and then this is plus x to the negative 1/2 dx. And now I can just use the power rule on each piece here. And, I don't actually need this. Let me just do this. So this is going to be x to the 5/2 over 5/2 plus this would be x to the 1/2 over 1/2, and then I'm going to evaluate this from 1 to 4. So I'm using that notation there, and so this will be 2/5, and then I'm going to plug in 4 here. So this will be 4 to the 5/2 plus, and this will be 2, and then this will be 4 to the 1/2, or square root of 4. Okay, and then that's plugging in just the 4. Now I got to plug in the 1. So this would be, when I plug in 1 into here, that's just 1. So this would just be 2/5 plus, and this would just be 1 as well, plus 2. So I got that, and so now I have a little math to do. This would be 2/5, and so this would be the square root of 4, which is 2 to the 5th power. So 2 to the 5th power is 32. And then make sure that's right. Yeah. Yep. Okay. And then this would just be 2. So this would be plus 4. 32. And this would just be plus 4 minus, and then this would be like 2/5 over plus 10/5. And so this would be 64 over 5 plus 4. I'm going to change this to 20 over 5 minus, and then this would be, it looks like 12 over 5. And so now I can combine, I got common denominator. So this is 8 over 5, combining those, and then 64, so 72 over 5. So if I did my math correct there was some math, that would be the exact value of the area underneath that particular curve. So that's cool. Okay, now this one here, I can't split this up over a common, I can't split a denominator up over a common numerator. Don't make that mistake. What I notice about this one is if I take the derivative of the bottom, I would get 2x, and I get that on top. So that when we talked about the substitution rule, we learned that the natural log, the log sub rule, or whatever we want to call it, it's really easy if you notice that the top of a fraction is the derivative of the bottom. Then you could just write the natural log of the absolute value of the bottom. So that's a nice rule there, and I'm going to substitute 1 to 3 into that. And so this would equal the natural log of 3 squared plus 1 minus the natural log of 1 squared plus 1. And so this would be like the natural log, 9 plus 1 is 10. And you could just say 10, because absolute value of 10 is 10, minus the natural log of 2. And if you wanted to simplify this, you could use property of logs. This would be the natural log of 10 over 2 which is equal to the natural log of 5. So it would simplify down quite nicely. And that would be the area underneath that curve, the exact area. Okay? So now this is actually one involving u substitution here. But that log sub rule, that's a really easy rule to remember. So you can go directly from here to here and plug these limits in. But you have to be careful with the u substitution. You got to also change the limits so that they are equal to the u value. So in the next video, I'm going to show you what I mean. We're going to use the fundamental theorem on integrals that use u substitution. So that will be our next video.